Thank you very much. There's like a, am I allowed to go all the way here? Okay. I'm not going here because I want to repeat the advertisement for Thursday evening. There's a play, you should all come. We have fantastic actors. It's if you want to know, it's a comedy. It's not a drama or something. It should be more or less an hour, but it's a comedy. It's nothing heavy and hopefully nothing boring. Hopefully easier to follow than a math talk. Okay, so recall that I was talking about property T, and let me just recall the following are equivalent. So TFI means the following are equivalent, and I'm going to make here G discrete. Of course, G is always a group. And I'm going to give you a list of equivalent definition of property T. So this is the original one, is that the trivial representation is isolated in G hat. Which there is a slight reformulation in terms of, so this is the Feld topology that we discussed last time. Any unitary representation with almost invariant vectors has an invariant vector. There exists S epsilon, where S contained in G compact, epsilon greater than 0, such that, so, okay, such that any, for any representation, either you have an invariant vector or for any G in S, the displacement of the unitary representation of any unit vector or any vector is greater than epsilon. So that must be obviously a non-zero vector in your Hilbert space. There is an equivalent definition which says that any finite dimensional representation is isolated in G hat, now in the space of, yeah, I guess, okay. And any affine isometric action on a Hilbert space has a fixed point, and so if you're in a Hilbert space, if you find a bounded orbit, you're going to find a fixed point. So that's the same thing to saying that has a bounded orbit. Because Hilbert spaces being cat 0, if you have a bounded orbit, you can find a barycenter for your bounded set, and that's going to be your fixed point. And any isometric action on a median space has a bounded orbit, but that doesn't necessarily give you a fixed point. Or, yeah. Okay, and given the questions that I had, I thought that I will say a few more words on the fact that if you're amenable and have property T, then you're a finite group. But before I do that, let me just make a comment. Oh yeah, first, the list of groups with property T. Let me just list of groups with T. So the one that were the motivation of Kashdan are the lattices in G where, so this is a lattice. So I mean that gamma is discrete, finite whole volume, and G is a higher rank, a simple Lie group. So Lie groups, yeah, simple and semi-simple Lie groups are Lie groups whose Lie algebra are either simple or semi-simple. But the point is that they're classified. So there is a list of those. So you can theoretically be lazy and not learn the definition because you could learn the list. So in the list, most of them are matrix groups, like SLNR, SPNR. So you can think of SLNR for n greater or equal to 3. And the rank, so there's an algebraic definition of the rank, but there is a geometric definition of the rank, which is the largest Rn you can isometrically embed in your group. So higher rank, or SLNR for n greater or equal to 3, means that you're going to find a flat copy, a copy of R2 within your group. In particular, you cannot be word hyperbolic because you have this flat piece. So they're never hyperbolic. And in the classification of Lie group, you also have a list of rank 1 Lie group. So rank 1 Lie groups, and the list is SON1, SUN1, SPN1, and F4 minus 20. And those are the isometries of the real hyperbolic space of dimension n. And so that guy you might have seen already, it's a space with constant curvature minus 1. And if you take a co-compact lattice, you're going to have a nice hyperbolic manifold, and your lattice is going to be a hyperbolic group. But if you have a non-co-compact lattice, it still has finite volume. It's a relatively hyperbolic group, meaning that you'll start finding flats in it, but they're very isolated ones from each other. So this one is the isometry group of the complex hyperbolic plane. Okay, I'm not going to really go into the definition. I'm going to wave my hands to describe it. It's a hyperbolic plane that you get. It's a hyperbolic space. Those are hyperbolic spaces that you get, and so they get dimension 2n because it's over the complex. But the thing is that the curvature is not constant -1 anymore. It varies a little bit between -0.5 and -1. But it's still a very nice hyperbolic space, and the co-compact lattices are word hyperbolic groups. And this is the isometry group of the hyperbolic space over the quaternions, the Hamilton quaternions. So, you know, you get C out of making R plus IR. Then you get the quaternions out of making C plus IC. And, you know, there's some difficulty that follow. For instance, it looks like a field, but it's no longer commutative. And if you iterate the procedure, you get a hyperbolic plane over the octonions, but then there's only you can only do one. The octonions are no longer associative, so it's a really an exotic thing. So they don't have property T, but those have property T. I'm not going to give the proof. I'm going to explain why those ones don't have, you're going to see why those ones don't have property T, but I'm not going to say anything about why those have property T, except that now you know that you have a nice class of hyperbolic groups with property T. And so it's good to know that we have a bunch of hyperbolic groups that can have property T. But what can you do with hyperbolic groups with property T? Hyperbolic groups all have this property, which is, say, SQ universal. And which means that SQ universality means that if I choose a hyperbolic group, and if any of you choose the worst possible group you can think of, I can produce a quotient of my hyperbolic group in which your horrible group embeds. So hyperbolic groups are SQ universal, meaning that for any gamma hyperbolic, any H finitely generated, H embeds in a quotient of gamma. So it's pretty clear if you start with the free group. You have a finitely generated group as a quotient of the free group. But so as a result, you see that any group embeds in a property T group. So being a subgroup of a property group T group is no information. Okay, any finitely generated group embeds in a property T group. All right, so this is really to say that being a quotient, being a subgroup of a property T group is no information. Okay, and I find it pretty interesting that the original motivation for Kashdan was to prove something using property T, but then most of the other result is you can't prove anything using property T. Now, there's a few things you can prove. I'll tell you a few more things you can prove using property T. But in many questions we ask ourselves in geometric group theory, many times property T is telling you that's not going to happen because this definition, any isometric action on a median space has a bounded orbit. It implies that any isometric action on a CAD0 cube complex has a fixed point. So it means that you cannot use any CAD0 cubical geometry to understand the property T group. Okay. Right. So back to the amenable case. Right. So recall that gamma amenable means that for any f containing gamma finite, for any epsilon greater than 0, there exists u which depends on f and epsilon, such that fu with u is smaller than epsilon. So yeah, so this really means that if f, a finite set you can think of it is a set of moves in your group. So really this means that u is epsilon moved by f compared to the size of u. Right, and we had the regular representation. And let me make a comment about L2 of G. So we saw in Genevieve's talk that L2 of G is L2 of gamma is a Hilbert space. But you might remember that you saw in some class or somebody told you that there are not that many Hilbert spaces. There's C to the power n, and then there's L2 to the power n. So why the hell are we saying L2 of gamma and we're changing the gamma? Because we know that this, in fact, is L2 of n. The reason why we write L2 of gamma, and we don't write L2 of n, even though we know it's the same thing, is because when you write L2 of gamma, you have your Hilbert space L2 of n, but with it, you have a bunch of unitary operators. So L2 of gamma is really a Hilbert space with a bunch of unitary operators. And because if you have L2 of gamma or L2 of something that has some structure, the structure will give you a bunch of you will give you a bunch of operators. And right, so the action, so if you have C in L2 of gamma, the action lambda G C, and now I'm going to say X, given by C of G inverse X, is just, so L2 of gamma is this, I always represent it like this, because because if your space is infinite, you need to go to 0 at infinity. So lambda g will displace this function. And so an invariant vector C is invariant, is an invariant vector, means that Cx is C of G inverse X for all G. And that will force C to be constant. But now a constant function that's L2 can only be 0. Otherwise, if it has a little mass, constant mass somewhere, it'll blow up. Okay, right. I'm just coming back to, and then you can check that the almost invariant vectors are going to be given by the characteristic function of u divided by square root of u, and this is going to be your almost invariant vectors. If I'm here, do we get no? Anyway, so these are going to be your almost invariant vectors. So that shows that as soon as your group is infinite, with amenable and infinite, you get a sequence of almost invariant vectors, but no invariant vector. And this is how you disprove property T. This is actually right. So this kind of shows that. So this also implies that if you have a quotient that is amenable. Oh yeah, this is maybe something that I wanted to say. Which is something that I will leave as an exercise. Well, I'm going to say proposition, but the proof can be done as an exercise. So if you have a short exact sequence of groups, and Q and both groups on each side have T, then G has T as well. But the converse is not true. Okay, so the converse is true for a direct product. But it's not true in general. But not true in general. And in fact, in general, you have Serre's theorem, which says that if G finitely generated so that the center of G, which I denote by ZG, like centrum. I think it comes from the German, such as the G mod the center has T, and the abelianization is finite, then G has property T as well. All right, so why is that result interesting for us, or for geometric group theorists? It's because of the following corollary. And here I'm really telling you a bit of a story that you just can take it as a story. I'm not claiming that you should really understand the math that I'm telling you. After the little story, I'll come back to really explaining some math. So this you can take it as a story. So the corollary is that if you take a co-compact lattice in SPN1 twiddle, which part of the story that I'm telling you is SPN1 is not, this is not simply connected. It has a it has a universal cover. And ST, but in fact, this gamma fits into a short exact sequence where this is Q, and this is a co-compact lattice in SPN1. So we said it was a hyperbolic group, and this is a central extension. And central extensions of a hyperbolic group are given by bounded 2 cocycle. Central extensions in general are given by an element in H2 in the second cohomology group of your group. In the case of hyperbolic groups, all H2 is bounded. So the extension is given by a bounded 2 cocycle, and hence, well, this is again an exercise that one can do. Gamma is quasi isometric to Z cross Q. And this shows that property T is not a quasi-isometry invariant. Because you have a group that does not have property T since it has a quotient, which is Z. And you have a group here that has property T because of those results. All right, so that was right, that was the few comments I wanted to make. Right, I also wanted to say a few words about, so on more groups with property T, list of group with property T. So this is not T, right? But then, yeah, so once Gromov also showed that if you take a hyperbolic group and you take a quotient by of this hyperbolic group using a really, really, really long word, then you get something that's still hyperbolic. So out of those hyperbolic group with property T, you get a bunch of hyperbolic groups with property T that are not necessarily those nice and theoretically well-behaved subgroup of a matrix group. Once you take those weird quotients, you can get stuff that are considerably, that I don't really understand, but that are considerably more difficult. The other interesting point that I want to mention is that higher rank simple Lie groups, there is like a really big theory going with it, but you can associate to them what's called a symmetric space. So they have a maximal compact subgroup. If you mod out, you have a very nice CAD0 space. So a manifold with non-positive curvature. So all those property T groups act very nicely on some CAD0 spaces, but they can never act on a CAD0 cube complex. So the CAD0 spaces that come from those Lie groups are very far from a CAD0 cube complex. So this is also to show that there is a wide range of CAD0 spaces that are, I mean, CAD0-ness doesn't tell you anything about property T, even though cubical CAD0-ness tells you that you cannot have property T if you act on it. Okay, right, so I'm not allowed to go up until the end. Can I? Okay, so here. Okay. Right, so let me say a few words about why SL3R has property T. And it's a sketch. So the first step is a lattice. So gamma has T if and only if G has T. And so this direction right. I'm going to say a few words about this direction. And in this direction is surprisingly more difficult. And arguably not that useful. But yeah, so this direction is interestingly difficult. Kajdan didn't discuss it. The first proof I saw, I think, is in Margulies' book. In the other direction, what you will do is, the idea is you start with a representation of gamma, induce it up to a representation of G, and then if this has almost invariant vectors, show that this will have almost invariant vectors as well, find an invariant vector, go back to the invariant to here. The difficulty is if you start with a representation here and you restrict it, since one is something continuous and something discrete, you might not see much of what you're doing. Okay, so to do this direction, you need induced representations. You need induced representations, and there is a, okay, I'm not gonna, so you need induced representation. There's a formula for it. Okay. That I'm not going to do, finally, because I want to do something else. Yeah, so So you start with pi, a representation of gamma. So the induced representation from gamma to G of pi is a representation of G, and almost invariant vectors are also found in the induced representation, and so T will give, T for G will give an invariant vector which is also pi invariant. Okay, so, all right, no, so that was YSL3Z has property T. So first you show that probability T goes down to lattices, and then what you show is, and then you have to see why, and then you have to study SL3R. So how do you study SL3R? First, there is, you need to study the following subgroup of SL2R. You're going to look at H, which is SL2R semi-direct product R2. So there is an action of there is the obvious action of SL2R on R2, and then you can do the semi-direct product. But what's interesting is that this semi-direct product kind of sits in SL3R. And how does it sit in SL3R? All right. Let me just do it here. Yeah, so the embedding, you can embed, so SL2R semi-direct product with R2. You can think of, you put SL2R here, you put R2 here, 1, 0, 0. And that's your isomorphism. This is how you see your group. And so if you look at this, and then you can look at this subgroup, S, which has 1, 1, 0, 0, 1, 0, 0. You can check that this is indeed a subgroup. And the point is that if you take, this is an important lemma, that if you take a representation of SL3R with S invariant vectors, so I want to point out that S is equal to R2, so it's pretty small in SL3R. And if you have S invariant vectors, then those vectors, in fact, it has SL3R. And and I think that this fact is a particularly neat fact. The proof is not very deep. It's really moving around vectors. I mean, it's not very involved. It's really a matter of moving around stuff. But it relies on the fact that if you take any of those, if you take any of the elementary matrices, they normally generate SL3R. See, because you take an elementary matrix, it has a 1 somewhere, you just conjugate, you're going to put the 1 everywhere, so you're going to generate everything. And if you have an action, if you have a group action, and you have an element that normally generates your group, or a subgroup that normally generates your group, and the subgroup acts trivially somewhere, it will force the whole thing to act trivially. All right, so once you but this is really an important comment. If you have a group that's normally generated by something, and the something act trivially somewhere, the whole thing act trivially. And right, so and to finish the proof, there uses a definition of relative property T. You have a subgroup G, and you say that the pair GH has property T. This is called also relative property T. Well, so it's kind of, you mimic the definition. So you're going to say that if any representation with almost invariant vectors has invariant vectors, has H invariant vectors. So it means that if you have a pair with itself has T, that's the same thing as saying that G has T, and also G neutral element always has T. And then, so to conclude property T for SL3R, so then it remains to show that SL2R semi-direct product with R2 relative to R2 has relative, and to do that, you make SL2R act on its unitary dual. So since SL2R acts on R2, it will act on its unitary dual. You look at the action of SL2R on R2 hat, which is R2, and you translate having almost invariant vectors in a statement about measure, and invariant vector, right, comes from the fact that that the Dirac mass at 0 in R2 hat is the only SL2R invariant measure. You look at SL2R acting on R2. What does the action do? Right, the action of SO2R is just going to rotate stuff, but SL2R is going to smash things. So it's kind of believable that the only measure that's going to be invariant is the Dirac mass at 0, because that's the only point that's not really moved. Okay, so that was right. So that was, yeah. Another list of group with property T. Okay, so here we have SL3Z as a lattice in SL3R. And another important class of group with property T is SLNQP, or and gamma acting co-compactly on X, the Ruhatitz building associated to SLNQP. So this I'm just mentioning because the way you prove that is using the paper I'd like to read next week. And the paper I'd like to read next week, so it uses the action on the building mixing properties. Yeah, and this is so. Let me just mention maybe the full results. Yeah. No, I mean not an intelligent one. Not one that doesn't go through. I have property T, and I'm going to follow that step. Yeah. But yeah. But yeah, that's really something that I would like to understand. Is if we can get a geometric proof for SL3R having property T out of this rather combinatorial proof of SL3QP having property T. It's a bit of an oddity. Many results that people have for SL3R or SL3QP, they mimic in a way what's happening. Just like similarly to when we try to do something for hyperbolic spaces, we understand what we're doing on a tree, and then we try to imitate what we're doing on a tree on the hyperbolic space. Just with this idea, we should be able, because math is like a perfect theory if we understand it, we should be able to kind of mimic what we're doing here on a building with a manifold, but there's results that explain you how to not do it. So but you know, okay. But since I can see that people want to see actions, what I'm going to explain now is how you get here and here from property T, how you get to action, and that brings me to the definition of, so this is, and G has T. And so if you want to have anti-T, which you also heard as Hager property or AT-manability. Then you also, I'm going to skip on that, but I'm going to just go here and say there exists a proper action. affine isometric action on a Hilbert space. And then you don't do the rest. And then there exists a proper action. So now we're going to see how from a unitary representation you go to an action. So let me just make this comment again on terminology, because I could see that the first terminology about property T was calling property T cache-down groups. And while I understand the need to honor the people who do great math, or who exist, or I don't know what, I think that when you give a name to something, it should be a name that says something about what you're naming. So if you say property T, even if you understood nothing about property T during my lectures, you might remember that there's a trivial representation isolated somewhere. If I had, say, cache-down group, and you understood nothing of my lecture, you get out with nothing. And so if I say anti-T or AT-manability, you might get out something, even if you understand nothing of the math. If I say Hager property, you really end up with nothing. So anyway, that's my speech about naming things, not with names of people whom you like to impress, but names of really things that show you, that say something about what you're naming. And also, naming something after somebody is a way of saying, well, the stuff that this guy did and that I don't really understand. So you might as well give a good name. Okay, yeah, so how do you go from unitary representations to actions? So yeah, what is an affine isometric action? So it's G acting on a Hilbert space. And this is where I think the terminology is kind of misleading, because it's not a linear action. You're not going to find, it's actually an affine Hilbert space. So it's a Hilbert space, but you ditch the zero and you just think of it as a set with an action of itself that you now think as a vector space. So if you have an affine action, an affine isometric action on a Hilbert space is what? Is a map from alpha, is a map that I call alpha from G. Now G is a discrete group. I'm going to ditch locally. Now it's just finitely generated. It's just a map to the isometry group of H. That's what an action is. It's a group homomorphism from your group to the isometry group of the place you want to act on by isometries. So, but then it happens so that just in the case of Rn or Cn, the isometry group of H decomposes as a semidirect product of H with UH. So each time you have an action, so H with UH, well, it's a semidirect product, it's a nice group, and you have a map, which now this is a group homomorphism, because it's just the projection. So if you compose your alpha with this just standard projection, here you're going to get pi. That's the linear part of your action. It's the unitary representation that we've been talking about. This is the linear part of the action. But then it's a semidirect product, so you have a section, meaning that you have a map. Okay. You have a map that goes to H, which is not a group homomorphism. It's still there. And this composition here is another part of interest is B. So this is, B is not a homomorphism. But a cocycle, meaning that I'm not going to go into the theory, but I'll tell you just the definition, meaning that it satisfies B of GH is equal to B of G plus pi G B of H. So B takes an element G and maps it to your Hilbert space. And it satisfies this equation. This equation is a rough reformulation that alpha is an action. If you write out the fact that alpha is an action and that and this map here, this is the equation you get. Now, what happens if the action has a fixed point? If the action has a fixed point, C in H, so it means that alpha G C is equal to C for all G in G, then C is equal to pi G C plus B of G. Oh yeah, I didn't tell you that, the alpha, the action is given by pi G C plus B of G. This is really out of spelling out whatever's in here. Pi is a unitary representation. Yeah. So if you have an action, because the action is a homomorphism into isometry group of H, and because H decomposes, the isometry group of H decomposes like this, well, if you compose your action with the canonical projection, you get a unitary operator. Yeah, here you get a unitary operator, which is a unitary representation. Yeah, you get your unitary representation out of taking your action and composing with the projection on the unitary part of the action. And that will decompose your action as alpha GC plus pi GC plus BG, which is right, your cocycle. Yeah. Yeah, exactly. Exactly. Yeah. Yeah, exactly. You get this because since it's an action, you need to have you get this equation. You get this equation out of alpha GH C equal to alpha G of alpha H of C. When you write out everything, that's the equation. That's the equation you get. Yeah. From pi and B, you recover alpha. Yes. From pi and B, you recover alpha like this. Yeah. If you have a unitary representation and a cocycle, then you can stick them together to get an action. Yeah. So it's really the same thing. Okay. So now we have our action, and we have a unitary part and a cocycle part. And let's see what happens if you have a fixed point. In the 15 last minutes, that's good. So what happens if you have a fixed point? Then xi is equal to pi g xi plus bg. So bg is xi minus pi g xi. And this is what we called a co-boundary. And yeah, so that brings me to another. Right. Okay. So so sometimes you see 5 rephrased as h1 of g pi is equal to 0. So this is exactly saying that any affine isometric action has a fixed point. Because this is the space of cocycles. So it's called, and this is the space of coboundary, and if you have a fixed point, your cocycle is in fact a coboundary. Okay, great. So okay, so how now do we go from isometric actions to median spaces, to Hilbert spaces to median spaces? Oh, yeah, just before I do that, let me, since I discussed anti-T, I can say that, yeah, the action alpha is proper. Proper means that if a sequence goes to infinity in the group, meaning that it leaves every finite set, it will go to infinity in the Hilbert space. The action alpha is proper, meaning that for any xi in H and any sequence Gn going to infinity, then alpha Gn xi, which is an element in the Hilbert space, so you can compute the norm in H. So that's a sequence that goes to infinity in R. But what does it mean to go to infinity if you have an action that's decomposed like this? This is never going to move because it's a unitary action. So this doesn't do anything else than having norm 1. If you want to go to infinity, you need your cocycle to go to infinity. So this means that for any sequence Gn going to infinity in G, then the norm of B of Gn goes to infinity in H. Well, this is in R, right? And so that's how you can go from from unitary actions with almost invariant vectors. So okay, this is how you go from unitary operators to actions. And of course, I skipped under the rug how you prove that H1 is 0 if you have a representation with almost invariant vectors, and you force it to have, the idea is like you have a representation with almost invariant vectors, and you get a bunch of co-boundaries that tend to 0, and out of that you get your co-boundary out of your fixed vectors. Anyway, so how do you go from so again, it seems much easier to show that something is proper rather than show that everything is bounded. Because if you want to show that you're AT-amenable or anti-T, you just have to find this one proper co-cycle. If you want to show property T, you have to look at all unitary representations. So to go from Hilbert spaces to median spaces, go from Hilbert spaces to median spaces. And back, I guess. You use spaces with walls. I mean, this is how Drutu, Haglund, and I did it when we did it. There is actually a shorter way using other stuff that I might discuss briefly. So right. So X space with walls, or wall space, is a set with a collection of partitions X is H union H complement, and H is in H and H complement. H is not a Hilbert space anymore. Okay, we'll just call it H like this. This is the set of half spaces. So you have a collection of half spaces, and you want it closed under complement. And you're going to have walls, which are a pair of half spaces. And you want that for any x, y in X, you're going to denote by WXY the set of pairs, pairs, I'll just call this W, such that X is in H and Y is in H complement. And you also want mu, a measure, on W, such that for any x, y in X, the measure of the set of walls separating X from Y is finite. Right. So this is the definition of a space with walls. So you need to have a bunch of partitions, and so that's it's a partition. So you can say when a partition separates 2 points, if you're one side and the other, and you want a finite measure on the set of points. So the classical example is X is the vertices of cat-0 cube complex. So a cat-0 cubical complex, I'll come back to that next time. I guess if you don't know what a cat-0 cubical complex is, you should ask me by next time and I'll explain to you. But I'll recall what is a cat-0 cube complex next time, but you might need to take a head start if you want to enjoy it. But anyway, so cat-0 cube complex, I think they're very nice. Oh, it's time to wrap it up. Okay, so cat-0 cube complex are very nice objects. You take cubes, like the cubes you would give to a child, like wooden cubes or something, and you glue them together. You glue them together without doing in the most naive possible way, so you don't smash anything, and etc. You look at the Euclidean metric on the cubes, and you want it to be cat-0, meaning that you're not allowed to create positive curvature. And so when you have a cube complex, you take an edge and you start cutting the edge along the cube, and you keep cutting across, you keep cutting perpendicularly across squares and cubes. And the magic of cat-0 geometry forces this procedure to separate your space into two pieces. You're not going to come back and cut yourself again. So I guess the easiest example is you take a tree. If you take a tree, you cut an edge, it will cut your tree in two pieces. So that's an example of space with walls, and you see that if you have 2 points, now you need to take only one wall per edge. If you have 2 points, you have a finite geodesic, so you have finitely many walls that separate any 2 points. So Hilbert spaces have a bunch of walls because, right, so, and the thing is that a space with wall, out of a space with wall, you can recover a median space, you can build a median space. And the Hilbert spaces have walls. I guess I can write it here. And, okay, no. So Hilbert spaces have walls. So what are your walls? Walls need to be a codimension 1 Hilbert subspace. So what's a codimension 1 Hilbert subspace? It's the kernel of linear functional. So you take a linear functional in your Hilbert space, take the kernel, you're going to get a partition, and all right. So I'm not going to write anything because I'm left with 1 minute exactly. So, but that I'll repeat next time. So your linear functional gives you a partition. The partition is given by a hyperplane, and both sides, if you have a metric because you're a Hilbert space, both sides are convex. You have one side that's convex, the other side is also convex. So when you have a space with walls, you can get a metric, or pseudometric first, out of deciding that the distance is the measure of the number of walls separating 2 points. That gives you a pseudometric. And if the walls you had were convex with convex complement, the metric you get is the same you started with. And in fact, Hilbert's, just as cat-zero cubical complexes and wall spaces are in fact the same thing, Hilbert spaces and measured wall spaces are the same thing as well. And I'm going to talk about that next time. Thank you very much.
Yes.
Yeah.
I did not follow the last part of this. So why?
Oh, yeah. So it was, it's normal you didn't follow. Nobody should have followed. It was too fast. So, okay. So why is it? So if you have, right, if you have relative probability, then what do? You take an almost invariant SL3 invariant vector. It's going to be almost SL2R semi-direct product R2 invariant as well, because this is a subgroup. And because of relative probability, it's going to be R2 invariant. And because of this fantastic lemma, which I think this is one of the best lemma in matrix groups, then you have an SL3R invariant vector. So start with a representation with almost invariant vector, restricted to the semi-direct product, use relative T to get R2 invariance, and then use this lemma to get SL3R invariance. Yeah, so relative T, this is really the part I didn't explain. There is quite a bit of analysis involved into understanding how you can translate relative probability T into understanding what are the invariant measure of the SL2R action on R2 hat. It's a bit of analysis, but for analysts is relatively standard.
Are there any other questions, comments?